This is part 1.3, and today I want to talk a little bit about corollaries of axioms, of the axioms of a group, obviously. So I remind you that we had very briefly, so I remind you the definition. So G, a group G, group G is a set plus operation, and operation is just this map from G times G to G, which we call multiplication, such that the following axioms hold. So the first one is that for every three elements, G1, G2, G3, G1, G2 times G3 equals G1 times G2, G3. So this one is called associativity. The second one is that there exists a special element in G called unit, such that for every G in G we have E times G equals G times E equals G. And third one is that for every G in G there exists G prime in G, such that G prime equals to G primes G equals to E, and this is called the inverse. So this is the inverse. And so I want to talk a bit about certain corollaries of these axioms, which are simple and straightforward, but still worth noticing. And the most complicated one will be related to associativity. So some corollaries. So let's start with obvious things. So obvious questions are, okay, this unit, is it unique, or maybe there are a few units in the group? So actually, unit is unique, and I will write these proofs very briefly. So proof will be just imagine, so E1, E2 are units, then we can multiply E1 times E2. And on one hand, because E1 is a unit, so E times G equals G, it is equal to E2. But on the other hand, E2 is a unit, so it equals to E1. And so we get that E1 equals to E2. That proves the uniqueness. So similarly, one can show that inverse is unique. And indeed, so imagine, so suppose we have G prime and G2 prime are inverses of G. So then we can look at the product G prime times G G2 prime. And on one hand, since G prime times G is unit, it's equals to EG2 prime G2 prime. On the other hand, by associativity, we can change brackets, and G2 prime is also a unit, so it's G prime E is G prime. And we get that they actually are equal to each other. So that proves that the inverse is unique. And actually, so just speaking about notation, so this G prime is usually denoted G power minus 1. And in a second, we'll talk about other powers, which is pretty what you might expect. So, so then there are some other things one can say. So there are several properties of inverses, and I want to give them as exercises. So sometimes I will say something is an exercise, and what it means it's actually kind of an important problem to do, but it's simple compared to usual homework problems in this course, and so I don't want to assign it as a problem, but if you see such exercises during the course, you definitely should spend time on them, because there are some simple computations every mathematician should make at some moment of his or her life. And so here is the exercise. So for every element G in G, we have G inverse is G. So other way to say it is that to invert an element, this is an involution. It means it's a transformation or a map, which when you do twice, you get the identity. So if you twice do the inverse of a map of an element, you get G back. And this is one thing, and another thing is for every G1, G2 in G, G1, G2 inverse, and that's interesting. So of course sometimes it might be equal to G1 inverse, G2 inverse if the group is abelian, but in general you change the order, so it's G2 inverse, G1 inverse. And that's also an exercise, and this is almost trivial. This is also very simple, but I recommend to do it and see where this change of order comes from. So this is something to remember, because this simple computation appears all the time in practice, and this reversing of the order, it is a bit confusing at times. So finally, very important cancellation property, it's called. Cancellation property. And it's very simple. The reason it deserves a special name is because sometimes it goes beyond. It's not true for groups only, it's true in some other cases, but we will discuss it in the next quarter. So it says that for every elements G1, G2, and H in G, if G1H equals G2H, it implies that G1 equals to G2. So proof is trivial. You just multiply on H inverse, you apply associativity, you move brackets, and you get it. So again, it's maybe a little exercise. And we'll see a lot of applications of this cancellation property. You'll also see one in homework. So again, the idea is that if you have some equality of elements in any group, you can always cancel them. And you know, it's not completely trivial in practice, because when, for instance, you are working with things like isometries of the plane, they are maps, and applying this even very basic operations can lead to interesting geometric consequences, and we will see it when we talk about symmetries somewhere in the middle of the course. So finally, equations x G1 equals to G2 and G1x equal to G2 have unique solutions. So what it means that you have an equation in a group. So you know that x times some element equals to some other element. Then you can multiply on G1 inverse, you will get that. So this is just equivalent to x being equal to G2 G1 inverse. And of course here you will see G1 inverse G2. And so the statement is trivial, but what is very important is that these two equations have different solutions. So because in general, in a group, you cannot change the order when you multiply, these two equations are completely different. And so this is why you cannot simply write a fraction. So maybe that's an important remark, is that if you just have a fraction like G1 divided by G2, that simply does not make sense. So if you have a general group, you need to say you kind of divide from the left or right. You multiply on G2 inverse here or there, and it may give different answers. So of course, for some groups it will be the same thing, but that's sort of more of an exception. So these are some simple corollaries, and so now let me go to a more involved story, the one related to associativity. And here the basic observation is that, okay, we definitely want to multiply not just 3 elements, n elements. And from here it's kind of obvious that brackets don't matter. You don't need brackets. You can put brackets in either way. You can change them, and that doesn't change the element. And I want to prove it. The proof is very straightforward, and then give a brief discussion of this principle from somewhat higher mathematical perspective. Okay, so now I want to explain the following idea. So if you have more than 3 elements, for instance, let's say 4, there are lots of different ways you can multiply them. For instance, this is one way, and say this one is another. And they differ by putting brackets in different way. And the claim which I will make is that these things are just equal to each other. So whatever way of brackets whatever way you put the brackets, you will get the same element in G. So let me formulate it in the following way. So proposition. So there exists a unique function from G times G times G n times to G. So remember, product is a map from G times G to G, which I will denote P, such that. So I want it to be just product of n elements. So the following 3 properties will hold. P of G equals G. So this is for n equal to 1. So it just does nothing. P of G1, G2 is G1 times G2. And finally, for every I greater or equals than 1 less than n, P of G1 up to Gn is the same as P of G1 up to Gi times P of Gi plus 1 times Gn. So what it means, of course, later on I will denote this function by the same thing without p. I will just write n elements multiplied. And this says that if you multiply n elements, it's the same thing as multiply first I in the same order, and then multiply the rest and multiply them. And it doesn't matter which I do you choose here. You can break your expression as much as you want. So, and this element, for instance, will be p of G1, G2, G3, G4. So the theorem is the proposition is very simple. So the proof is by induction, and it's almost trivial, but I still want to do it because, you know, when you learn algebra for the first time, of course you need to get the big ideas, concepts, examples, and so on, all the fun stuff, but also you need to become good with details, and especially sometimes when the details are sort of a little bit tedious to work out, it's good to have some patterns in your mind how you can do it. So let me formally prove this theorem, so of course it's completely straightforward. So proof goes by induction. And as usual with induction, we want to consider first on n. So first the base, and the base will be just, so n equal to 1, and n equal to 2 is just, there is nothing to check, this property is completely obvious, so obvious. And n equal to 3, so the only interesting case for n equal to 3 is to take I equal to, you can take I equal to 1 or I equal to 2, and you get exactly associativity. So associativity is just our proposition for n equal to 3. And then for other n we do by induction, so assume it's known, assume that n minus 1 is known. And of course, I mean for every I, right? And so now let me prove for n from here. So then we have exactly that to prove, and we can say that P of G1, Gn. So I need to define it. So define P of G1 Gn as P of G1 times and so on times Gn minus 1, which I can do because my function for n minus 1 already exists and is unique and satisfies this property, times Gn. And since this is just the property I want for n equal to n minus 1, so this is the only way it can be. So we just remark that so P for n, let me denote it Pn, maybe this P when you have n inputs, this P is unique. So it's unique because just as a corollary of its property, you immediately get the definition. So this P is unique, and then for I less than n greater or equals than 1, I can write my P of G1 Gn. So it equals to P of G1 up to n minus 1 times Gn by my definition, which equals to P of G1 times and so on times Gi times P of Gi plus 1 up to Gn minus 1 in brackets times Gn. And this is my induction step. And finally, I can just switch brackets. So I can say that that's the same thing as P G1 up to Gi times the remaining part, P of Gi plus 1 to Gn minus 1 Gn. And here I just use that for every, so I know that the number of arguments here is less than n, so I can again use induction. And this gives me that this is P of G1 up to Gi times P of Gi plus 1 times Gn as we want. So we get exactly this statement. That proves the step. And that finishes the proof of the proposition. So you see basically what I did in somewhat colloquial language. I just said, okay, you have n elements, let's just multiply first 2, then on third, then on fourth, and so on. And then by induction, I proved I can change brackets as I like. So, of course, what it means that in any group, this sort of multiplication of n elements is a bit of a simple story. But let me just add here some more maybe interesting observation. So one can still try to have a look at what exactly happens. So let's for instance take 4 elements and let's write down all possible bracketing expressions, they are called. So we'll have G1, G2, G3, G4. And if you look at this element, you see that there is 2 ways you can change brackets using associativity. So one of them is to move from here to, so let me kind of immediately draw the eventual picture I'll have. So using associativity, one can move brackets in this part, and you will get G1 times G2, G3 times G4. Or one can move them, these big brackets, to G3, G4, and one gets G1, G2 times G3, G4. And then one can move these small brackets here to G1, G2, G3, G4. And here one also has G1, G2, G3, G4. So what I got is a graph. So I hope all of you have some idea what a graph is. If not, you need to Google or like at least look at some pictures. So we will see a lot of graphs graphs in these lectures, and actually in the end of lecture 1 we'll discuss graphs as well. So graph is some picture where you have points and connecting by certain curves, picture on the plane, and this is a way to present an abstract structure of a certain subset inside a product of a set with itself. And so it was discussing, but I'm not going to do it right now. So here we get a graph where vertices are these bracketing expressions and edges are apply associativity. So like how you can move from one expression to another using just associativity axiom of a group. And this picture proves our theorem for n equal to 4 simply because if you want to show that this one, for instance, equals to this expression, you just need to apply associativity twice. So you might wonder, okay, so because of this simple theorem, in a group this all doesn't matter, all elements will be always the same. But like still it's interesting how that happened, and what happens if I take 5 elements instead of 4, for instance. What picture do I get? And the theorem approved means that the graph I get will be connected, meaning you can connect any two points by a path, and this is exactly the number of times you need to apply associativity to prove the corresponding equality of two expressions. And so people started to study these graphs, and let me kind of tell you the name for the structure. So it's called something called associahedron. Associahedron is the structure you get if you study that. And what it is, it happens that if you just draw all these points, you get a graph which is actually a graph of edges of a higher dimensional polytope. So even for n equal to 5, you will get here a polytope which is a 3-dimensional with 6 5-gons as faces and 3 4-gons. It's very beautiful. It's called associahedron or stash of polytope. And it appeared first in topology, so we can look a little bit at history of the subject. And already the number of bracketing expressions of its vertices is interesting. It's called Catalan number, and it's related to many other counting problems in mathematics. And let me point out that there are structures in math where associativity doesn't hold. So it holds in many cases, and almost throughout the course we will see everything we'll see will be associative. So whatever we multiply will have this property, not only groups, also fields and rings and other stuff. But in general there are objects in mathematics which are not associative, and there the structure starts to matter a lot. Okay, so this was the third part of the lecture. In the next part I want to consider a few interesting examples.